How did that work?
Good morning, everybody. We are about to begin this morning's event, so please, if you managed to get coffee before we ran out, great. Otherwise, I believe we still have some decaf. If you could find your seats, enjoy your breakfast. I'd like to welcome you to another sold-out Washington Clean Tech Alliance breakfast event this morning. My name is Jacobson. I will be moderating our panel today. I run the energy program at the Washington State Housing Finance Commission. Before I begin, I'd like to thank our volunteer committee that planned this event, led by Andrea McFadden. A special shout out to Sharon, who is she in this room? If you see her, say thank you, because she took all of our vague amorphous concepts and brought it into a very highly scripted, highly organized event and made all this possible. As we begin our event, we'd like to recognize our industry sponsor today from Unit Energy Technologies, and I'll let Russ say a few words.
Good morning. We at Unit Energy Technologies are a grid-scale energy storage company. We're up in Mukilteo. We were established in March 2012. We're now 35 people, hopefully scaling up to 100 people. Today is an auspicious day in the energy storage world, as, for example, Craig knows. Today is under the Washington Clean Energy Fund Smart Grid Grant Program, the day that utilities turn in their applications for a $15 million matching program. So this is quite well timed, and looking forward to the presentations, the discussions. I am substituting here for Susan Betcher from Perkins Coie. I want to thank them in particular for hosting us here and to kicking off this whole series of breakfast talks that we'll have to close this year and go into next year. So with that, Avi.
Thank you, Russ. All right, now my goal is to keep us as on time as possible moving forward so that we will have time for questions after all of our panelists present. One thing to note that if you are going to be tweeting this event, we'll be using the hashtag that you can see up on the screen, the WCTA events. And if you don't want to search or follow that hashtag, you can probably just follow Tom or Ross, and you'll see plenty of tweets about this. Our first presenter today is going to give us a general overview about battery technology and put this whole event in context for us. Now, Grant Norton is the Dean of the Honors College at Washington State University and a professor in the School of Mechanical and Materials Engineering. Currently, he is working on developing new nanomaterials for batteries and fuel cells with support from the Office of Naval Research, the National Science Foundation, Boeing, the Joint Center for Aerospace Technology Innovation, the Center for Integrated Nanotechnologies at Sandia National Laboratory, and the Washington Research Foundation. Dr. Norton.
Good morning, everyone, and thank you for the introduction. It's a great pleasure to have an opportunity to talk with you this morning. So I'm going to start by doing Batteries 101. I'm sure where the oh, hang on, there we go. I'm not quite sure where to point the clicker. Oh, there we go. So I'm going to do a Batteries 101 for the first 15 minutes, and the idea is to really give a very broad overview to battery technology to put the next three presentations into a kind of context for you. So this is really assuming that you know next to nothing about batteries. If you know more than next to nothing, then I apologize for any redundancy. And as this is finals week at WSU, of course I have to give you a test afterwards in the tradition of an academic institution. So batteries form one example of what we call electrochemical storage. So the whole thing that we're trying to do, the one thing that we're trying to do with electrochemical storage is to convert chemical energy to electrical energy. And so it's the mechanism that we do that, the efficiency with which we do that, the way that we do that becomes the different types of battery and electrochemical storage technology. The concept is really very, very simple. And one of the things that I look at in terms of engineering and technology is how long a concept has been known to how long it actually takes to be a market component. And if you look at batteries, electrochemical storage in general, we've really not made a lot of progress in almost 200 years of knowing about it. And so the history of the battery, or the electrochemical cell as it was called, dates back to 1800. And Alessandro Volta, the gentleman that's shown on the left, is the person that came up with the idea of this and built the first battery. So he's often described as the first useful professor, because up until then professors just studied philosophy and theology and these sort of things and sat in ivory towers. But Volta actually came up with something that was a technology and turned out, of course, to be very useful. So the innovation was that he realized that if you had two different metals and you separated them by a liquid, that you could generate an electrochemical potential, you could generate a voltage. So what he did is he took zinc, he took copper, he took a piece of cloth that he soaked in salt water, and then he separated them. And he generated a voltage. And he could stack all of these together, and this is his actual instrument, it's in a museum in Europe, and he actually then generated a voltage. So the chemistry is very simple. So, I know that it's very risky to use equations and very risky to use chemical formula, but the chemistry is very simple. So the zinc just goes from zinc to zinc ions and releases electrons. And those electrons react with hydrogen, and that forms hydrogen gas. And so there's an exchange of electrons. So the chemical reaction generates these electrons. And these electrons are what then does the work. And the difference between the two metals, in Volta's case the zinc and the copper, determine what the cell voltage is. And that cell voltage is 0.76 volts. Now the relevance of that will become apparent later on, and why we want to go to much higher voltages than we're currently at right now. I think I'll probably need the next. So conceptually, this is very simple. I mean, as I said, this is not rocket science. And even my son in second grade is there building his lemon battery, which is quite a good battery. It generates a quite reasonable voltage. Certainly it generates as much voltage as Volta's battery. So it's just three basic components that we have to play with. We have the anode, which is the negative electrode. We have the cathode, which is the positive electrode. And then we have this electrolyte, which is this solution or the liquid, or it could even be a solid, that allows these ions to move back and forward, but is an insulator for the electrons. So the electrons have to do work as a result of this chemical reaction. So you all know that there are different types of battery, and the different types of battery are just related to variations in the anode and the cathode and the electrolytes. There's only three things that we can change. It's not like we've got this very, very complex multi-functional equation. We've got three variables. So we can classify batteries into two simple categories: the primary battery or single-use battery, which you dispose of when you finish, and the secondary battery, which can be recharged. So you have multiple uses before the battery finally degrades. And so there are examples of very common batteries that you're familiar with that fit into those categories. One of them is the alkaline battery. And you can see, even though the chemistry is more complicated, all we're doing is generating electrons on one side of the battery and moving them to the other side of the battery through an external circuit. So in the case of the alkaline battery, that reaction produces 1.5 volts, which is twice the voltage that Volta was getting with his simple zinc copper battery. And the materials, the anode is zinc, On the cathode, it's manganese oxide, it's made as a paste, and the electrolyte is potassium hydroxide, which is like caustic soda, and that's why these are called alkaline batteries, because that's an alkaline material. In the rechargeable side, you've got this cadmium battery, nickel-cadmium battery. But you've got exactly the same thing. The cadmium is reacting to produce electrons, and those electrons are being consumed on the other electrode, and that's completing the electric circuit, and that produces 1.4 volts. So what's the difference between the primary battery and the secondary battery? The difference is that the reaction in the primary battery we can't reverse. So once we form the product, we can't get back to the original state, so we have to throw the battery away. With the secondary cell, we can apply the potential in the opposite direction to drive the reaction back to the beginning. So we end up with what we started with. But of course, nothing is perfect in this exchange, and so over time, the battery degrades. It holds less and less charge, it's less and less efficient, and eventually we have to dispose of it. You do. So how do we compare batteries? So what makes one battery better than another battery? So electrical energy, the electrons that are produced by the chemical reaction, they do work. And the work is proportional to the cell voltage. So the higher the voltage, the more electrical work we can do. So battery designers are always trying to make the highest possible voltage so the cell can do the greatest amount of work. And the cell voltage is determined by the difference in the potentials of those two electrodes. So if you were to go to a chemistry data book or go to Google, you know, everyone's real reference source, you would find the electrochemical potentials for almost every single reaction, an anode reaction, a cathode reaction. You combine those together, and that's going to tell you what the potential is for the final battery cell. So it's really the electrodes that differentiate one battery from another, or really the difference between those two electrodes. So how do we compare them from a scientific point of view? What we use is we use a Ragone plot, and David Ragone's a professor at MIT, and he developed this way of comparing energy storage devices. So really you can put any energy storage device on these charts. You can put flywheels or batteries, whatever you want. But it's a plot of energy density against power density. And what I've done is I've just taken a small part of the Ragone plot and compared some different batteries. The lead acid battery, everyone's got one in their car. The nickel cadmium, everyone's got one in their power tools, and rechargeable battery. And then the lithium ion battery. So when you look at the plot, you can see why people are interested in lithium ion batteries, because not only is the energy density higher, this is the amount of work the battery can do, but the power density is higher. This is how quickly it can do the work. So as you move on the Ragone plot to the top right-hand corner, you're getting, essentially for the consumer, a better and better and better battery. Now, the important fact about lithium is that all the elements, it's the most easily oxidized. And what we mean by that is it likes to lose its electron more than any other element. So this is very good for batteries, because you want something that wants to lose the electrons, because those electrons are then going to be free to do the electrochemical work. Okay. So lithium ion batteries. So this is where we're talking now about some of the current battery technology. So now we've got two different electrodes and we've got an electrolyte. What we're moving through the electrolyte are the lithium ions. Now, if you look at the conventional technology, this technology you've got in your phones right now, you've got carbon on the anode side and you've got lithium manganese oxide or lithium cobalt oxide on the cathode side. And they're separated by this lithium fluorophosphate, which is a chemical well known to Boeing and early Apple inventors related to its instability and flammability in lithium ion cells. And if I add up the two half-cell reactions, which again isn't rocket science, my son can add these two up. If I add 3.05 and 0.59, I get 3.6 volts. And that's the voltage of a lithium-ion battery. But we want to get more. Remember, we want to get more volts to do more work. So a lot of the technology is trying to push that voltage as close to 5 as we can. So of course we know there's lots of applications for lithium-ion batteries. We go to the next one. So the other aspect I want to just briefly touch on, because it's relevant to one of our speakers, is fuel cells. So a fuel cell is another example of electrochemical storage, and this is also known as a flow battery. So the term flow battery and fuel cell are synonymous. And this is a battery, essentially, that has an external fuel source. And again, these were developed a long time ago. 1842 was the first fuel cell, and Sir William Grove was a useful lawyer that actually was the person that developed the concept of a fuel cell technology. So by 1842, we had both useful professors and useful lawyers. And you can see now history has reverted, and we probably have neither of them particularly useful. But after 1842, both of them were very useful in terms of developing technology. But it's an electrochemical cell. We produce electrons from hydrogen, and we consume those electrons with oxygen, and the product is water, and the cell voltage is 1.2 volts, which is unchangeable. For that reaction, we can never change the voltage. It's always 1.2 volts to generate water. Okay, next one. But we have 3 basic parts: the anode, the cathode, and the electrolyte. Okay. In the case of the original fuel cell, the anode and the cathode were exactly the same material. They were platinum. And the electrolyte was sulfuric acid. So this was a technology problem of how we could commercialize this with those 2 materials. And as for different types of batteries, there are different types of fuel cells. So I think Sean's going to talk a lot more about the proton exchange membrane. Here what we're doing is we're exchanging hydrogen from one side of the cell to the other. The technology I'm going to talk about at the end of the morning presentation is about the solid oxide fuel cells, where now we're exchanging oxygen. The voltage we get is still the same, and we get the power by combining many of these individual cells together. And of course, even though it doesn't seem like it, there are actually lots of applications for fuel cells right now, and there are lots of potential applications for fuel cells in the future. So I think, as Sean's going to indicate, I think this is really a very important technology. Next one. So I just want to finish this section of the presentation by just combining fuel cells and other technologies on this Ragone plot. So both of them are electrochemical cells, and you can see the fuel cell is in that very top left-hand corner, which means that we've got lots and lots of energy, but not so much power. The lithium-ion battery is where it is, kind of heading in the right direction towards the optimum combination of power and energy. And then you've got traditional capacitors, which have great power, but very little energy. And of course, you can see I've even put flywheels on this plot. But the point I want to just leave you with in this 101 section is look at the state-of-the-art battery on the left. I mean, it's really primitive after 200 years of technology. And you look at what we've done with the integrated circuit after only knowing the technology for 50 years. You can see how the technology now for integrated circuits is almost unrecognizable from how we started in the early work in Bell Labs. The batteries look basically the same as they did 200 years later.
Thank you very much, Dr. Norton. Now, also, just have to point out, as far as useful lawyers, they were kind enough to host us. Some of them may even be playing business development roles in battery companies here in Washington, and you may even occasionally find one moderating your panels. They're everywhere. So as we're moving into our panel, shortly you'll see a theme of going in order from big to small applications of battery technology, going from the utility scale to more commercial industrial, and then concluding with where we see the future of consumer applications. You know, say, what you see in your phone right now, or your next coming phone. So questions that we've asked our panelists to address, and to keep in mind as you're looking at this, is what are the position of storage batteries and energy storage in your market now? What's coming in the next 2 to 3 years? What do you see in the near future, that sort of 10-year out window that you're hoping to see developed? the number one opportunity in your sector, and the number one barrier. And these barriers could be anything from technology, marketplace, policy issues, and so on. So beginning with the utility scale, we're going to be inviting Craig Collar. Craig is the Assistant General Manager at Snohomish County Public Utility District for Power, Rates, and Transmission Management Division. His areas of responsibility include power scheduling, short-term and long-term resource planning and resource development, power and transmission contracts, rates, energy risk management, load forecasting, and NERC compliance coordination activities. Craig is a graduate of Montana State University, which is home to the world's greatest dinosaur museum. I mentioned that because I was there last week. And he's also a former Navy man, but we're glad to have him anyway, mostly because I count at least 3 sailors and there's only 1 former airman standing up here. So, with that, Craig.
Okay. All right, well, thanks. Good morning, everybody. You never hear anybody say useful engineer. I'm just going to assume that means that all engineers like me are useful, so we won't need the little precursor. So quickly, I'm just going to talk about energy storage from a utility standpoint, some of the challenges that we see, some of the opportunities associated with those challenges, and then some of the ways in which we hope to be a catalyst to help overcome some of those challenges and really transform the energy storage industry into something that can really provide technology to utilities in a way that's much more cost effective than might be the case today. So there's a lot of different use cases for energy storage. I'll just kind of talk about one that's near and dear to our hearts at Snohomish. We currently don't have any carbon fuels in our portfolio at all. We seek to meet all of our load growth first with conservation and energy efficiency, and then with new renewables. So as you can see, we're mostly a hydro-dominated utility right now, but all of our renewable portfolio compliant energy mostly comes from wind. And you see here in the chart, this is a graph over the course of about a week, I think, of what our wind portfolio in the upper left-hand corner was doing. And then the bigger portfolio of wind on Bonneville's balancing authority was doing at exactly the same time. And you see 2 things here. One is that you can go from no wind to a whole heck of a lot of wind within a very short period of time, a matter of hours. In fact, in the slide on the right, or on the left, you see that wind in our service territory in our fleet went from 0 to about 30% of our load in a matter of a couple hours. And the problem is that in the Washington area, the Northwest area at least, if you kind of overlay those charts on each other, you see there's just not a lot of diversity there. So even if we had lots of transmission moving this wind wherever it needed to be, the wind's either all there at the same time or it's not there at all. So storage obviously is one potential tool that could help overcome this. So that's not the only use case for energy storage as far as utility goes. There's lots of other ones that we could spend a lot of time talking about. Voltage support, peak shaving, infrastructure deferral, a whole number of things that really hold a lot of value for utilities. And so far to this point, really, hydro has been really the only large-scale source of energy storage that's out there. Not only pump storage facilities, of which there are some, but really just the storage that's inherent in the reservoirs behind the large dams on the Columbia. Really, that's how we integrate that wind right now. We use our slice of the Federal Columbia River system and the storage inherent in it to integrate that wind. But we're at the point now with about 8% wind in our portfolio and the amount of capacity the federal system can provide that even if we had more wind, it wouldn't do us much good because we couldn't integrate it with the resources that we have now. But we're encouraged by the potential that batteries hold for smaller, more scalable, more relocatable energy resources in a way that could really be tailored much more to what a utility's needs are. The problem is they're way too expensive right now for utilities to use, except in some very specific kind of niche opportunities. And also, although batteries hold the potential for some of those other attributes I talked about in terms of modularity and scalability, that potential really isn't being unlocked right now. There really isn't a mechanism to take advantage of that in a way that's really going to move the needle significantly for utilities. And what this results in is sort of this big gap between battery manufacturers and what could be one of their key customers, utilities. So you got lots of folks out there all over the world building batteries, a lot of manufacturing scale. You have a lot of utilities who could use these things. There's some good use cases for them, provides a lot of value. But frankly, there's no easy way for battery manufacturers to link up with utilities and actually turn their products into something that we can really use in a cost-effective way. you can sort of contrast that with, say, transformers. For transformers, you go buy them out of a catalog. There's a very well-developed supply chain. They're standardized into our system. We buy them, we plug them in, we know they're going to work. There's nothing like that for energy storage right now. Every project is sort of a one-off deal. So the implications for this are probably self-evident. One is that right now the battery-based storage industry for utilities is very, very small. The ones that are out there you tend to hear a lot about because they're a big deal, but there's really not very many of them, particularly when you consider all the utility infrastructure that's out there. And most of the projects you see are either ones that are for a very specific use case or some kind of a learning or an R&D project. And frankly, as we looked at the landscape, we just didn't see a lot going on that was really going to change this. We didn't see a lot going on that was really going to move the needle in terms of really transforming this industry. A lot of great work going on in terms of battery technology, some work going on to bring down the cost of batteries, but these really are sort of incremental things relative to this larger challenge. So as we looked at that and talked to folks, a lot of folks saw the same sort of landscape, but again, we didn't see the activity going on that was going to fix it. So working with a number of folks here in the Puget Sound region, we came up with what we've called this modular energy storage architecture to really attack that standardization and architecture piece of the puzzle to hopefully establish that really well-developed supply chain, just like we have for all the other stuff we buy for our infrastructure. So part of the thinking of the genesis for this, just a useful example, is when we first started looking at energy storage, we went out and got some quotes for kind of neighborhood community energy storage devices, somewhere in the range of 24, 25 kilowatt hours. So basically what you get for this is sort of this black box, about the size of the one you see there. It could be patented on a neighborhood, and it costs you about $100,000. Not a lot of energy, not too useful for utility. You need a whole lot of these things, and pretty expensive, particularly when you consider that you could buy a Nissan Leaf with pretty much exactly the same amount of energy storage in it for $35,000. So you get all the same energy storage, you get a car, plus you get $65,000 left over. So there's a lot of reasons for this. It's not just the fact that the car is engineered for scale. That's a big one. But there's a supply chain in the automotive industry. I mean, when they start building stuff and designing things, they have they start with the end in mind. Where again, these energy storage projects are sort of one-off deals. So just to spend a few minutes about what this MESA project really is. Next, please. So we're going to have to click through this one a little bit, but if you think about what the components of an energy storage system really are, of course you have the battery, which we talked about. There's a lot of great work going on there. You also have the power conditioning system, so the transformers, the inverters, all the kinds of things that are going to take the output of that battery and turn it into useful power energy for utility. And there's a lot of good work going on there, but that's a pretty mature industry. But importantly, what you really don't have well established is sort of the control system for these things, the architecture, the communications, the standardization that will make these things talk to each other seamlessly in a way that's going to be useful for our use case. And what you'll find as you talk to other utilities who've done significant scale energy storage systems, they don't put this on their website, but if you talk to them, this is where the wheels sort of start to fall off the thing. This is where part of the real difficulty comes. Hooking the batteries to the PCS system, not that tough, but making them work together in a way that's really useful and automated is a big deal. And of course, the energy storage system has to connect to the broader architecture, which includes, importantly, one more click, all of the systems that we have at the utility. So it's really not enough for the batteries and the power conditioning systems to work together. But really the important part is that stuff's got to connect to our systems, to our supervisory control and data acquisition systems, to our distribution management systems. If every time you do an energy storage system, you've got to build that connectivity and communication from the ground up, we're never going to get to where we need to be. This needs to be a plug-and-play kind of thing for utilities, for them to really, for these kinds of systems really to become a ubiquitous tool. We'd envision, a future where every time we build a substation, we would install 2 to 4 megawatt hours of energy storage, and it would just become a standard way, the way we do business. And someday with 80, 90, 100 substations, you end up with 200, 400 megawatt hours of storage. That's enough to do something with. That's going to move the needle. So we've kind of talked about what utilities really want here. some of the standards that we think are applicable in this world are not just the physical and the electrical standards, but importantly the communication standards. And a good analogy is probably the PC industry. You know, you think of USB standards, Ethernet, Wi-Fi, Bluetooth, all these enablers that have really helped the PC industry take off. The same kind of thing needs to occur in the energy storage industry, and that's what this modular energy storage architecture project is really all about. That's its goal, is to really transform the energy storage industry via that architecture and communication standardization. So here's the team we put together for this project. It's not everybody, but some of the bigger players. We'll be working with Alstom out of Redmond. They're currently our SCADA provider, so important that they're on board with this MESA effort. One Energy Systems out of Seattle here. I think I saw Tim Melling here earlier, who's with One Energy. The University of Washington's working with us. We're awfully excited to have Uni Energy Technologies as part of this project. They're right in our service territory in Mukilteo, and really part of our goal in this whole thing is to help Russ sell not just dozens or hundreds of these units, but thousands, tens of thousands of these things. I mean, that's really the vision that we're trying to help fulfill. And then Parker Hannafin will be providing the power conditioning system. So what this will hopefully next year in 2014 result in is about 2 to 4 megawatts, several megawatt hours of energy storage capability installed at 2 of our different substations up in Everett. Not just for the capability that those energy storage systems will result in, but really to prove out the MESA concept, to show the industry how this works, what the value of it is, and hopefully to get even more and more players on board in the standardization effort. And this last slide here just reinforces some of the goals that we've talked about throughout this presentation, what we're really trying to achieve with MESA. And I think given the time, I'll hold off there and hopefully have a chance in the Q&A to talk a little bit more about it. Thanks.
Thank you, Craig. And it's only fitting that I introduce our last panelist. Well, I've been relying on a app that takes advantage of cloud storage to sync across multiple platforms and applications. Right here. Also, I'm excited to have Sean James here because ever since reading about some of the research and work that Microsoft's been doing in the data center space, I've been hoping to bring them in to present and sort of talk to our membership about what's been going on. We don't think about it, but this phone, this iPad, a lot of the computers, and a lot of the email, everything else we rely on, it's not a small phone. It's a giant data center somewhere far away, hooked up to lots of generators, backup power, and 2% and growing consumption of U.S. electricity is all in data centers right now. Something to think about. So, there we go. So, Sean is responsible for research and developing new data center efficiency technology for Microsoft's Global Foundation Services Group. GFS provides the foundational cloud infrastructure for over 200 Microsoft online and cloud services for consumers and businesses worldwide. Sean drives new data center technology for Microsoft's next generation data centers, including the evaluation, development, and testing of it. And not only that, Sean has graciously volunteered to move the slides because our little remote control has not been working. So there you go, Sean.
Thanks, Amy. Yeah, they brought the Microsoft guy here to run the keyboard, so that's one thing I can handle. So thanks for the introduction. I love my job at Microsoft. I probably have the best job at Microsoft because I'm able to play and really get into R&D and work with folks in academia and industry and come up with brand new technology that's really cutting edge. And if it doesn't work, that's great. That's success. We've proved that something doesn't work. That is unlike any job I've ever had before where everything has to work at all times. So I love my job. First of all, everybody here probably knows what a data center is, but if not, let me just briefly tell you what we're talking about here with the data center. Every time you go online, every time you go to a web page, you're actually downloading that file from another computer. It's just like the computer that's in front of you. There's a processor, and there's RAM, and there's a hard drive. Unfortunately, when you have millions of users, you need thousands, hundreds of thousands of computers to serve all that traffic. And so we call those special computers servers. It's a fancy name, it's just a computer, just a computer. So what does all computers need? And most people in here have laptops. Well, they need energy, and they need to be kept cool. So what I'm going to talk about today is I'm going to tell you that how we are currently delivering the online traffic to you is very, very inefficient. And I'm going to tell you the reason why, and I'm going to tell you what we're doing at Microsoft to try to fix it. First of all, the analogy of your laptop, I'm going to use that throughout the whole presentation today because it's got batteries in it, it's got energy conversion, and it's basically a mini data center. I'll tell you why. First of all, oh, changing the wrong computer, see? First of all, I want to talk to you about why is the way we deliver internet traffic to you so inefficient. This is a diagram that shows you all the losses in the energy. So when you go to Bing.com, Google.com, and you want to search for a cookie recipe, if it takes that server 1 watt to come up with that file, well, the power plant supplied 100 watts onto the grid. I'm going to tell you why. All the way on the left, you start out with some kind of a fuel, chemical energy in most cases. Right off the bat, at the power plant, you lose about 2/3 of that. Now, I know some power plants are more efficient than others. That's basically the grid average. As you get into transmission and distribution, and I know this slide's kind of hard to read, so I'm not trying to explain it here. Through transmission and distribution, you're going to have more losses. And it's basically as the electrons are flowing through the wire's getting hot, so you're losing energy in the form of heat. Once it reaches the data center, right off the bat, we have to keep everything cool, so we lose a bunch of energy in all the air conditioners and fans to keep all of the servers cool inside the data center. There's lighting, UPS, uninterruptible power supply. It's basically a huge battery bank. Now, when we looked at the chart earlier, we saw this plot between energy density and power density. In data centers, we need a lot of power density, not necessarily energy density. We only need to keep 30, 50 megawatts online for a few minutes. It still requires a lot of batteries. And since these are mission critical facilities, most data centers you go into, 99% of them are going to have the good old lead acid type battery that's in your car and that's been around for many, many years. And there's a lot of issues with that. I'll talk a bit about that. The power supply, so right in the server, in the analogy with your laptop, that your power cord that goes to your laptop, there's a box about midway down, and it gets warm. It's warm because there's energy conversion going on in there. You're losing energy through that heat. Same issues happen throughout the entire data center. Anytime you transform the energy for the power for whatever reason, changing voltages in the power supply, they're actually changing from AC, alternating current, to DC. The underutilization in the servers, just the fact that you have all this computing capacity in your laptop and in the server, you're only using a small portion of that, but all of the basic systems are all still running at a fixed point. So the fans are always running, the BIOS is always in there running. So there's some losses there, and just inefficient applications. Anybody can write code. If you can go online, you can quickly learn how to write some code, but the trick is to do it very, very efficiently. Probably some of the most efficient computers are in your pockets. Our cell phones. When a developer writes a program for a cell phone, they need to they need to account for power efficiency, because if you've got a great application, but the minute you turn it on, your battery only lasts an hour. That's not a very good application, so it needs to run very, very long. So what's going on inside the data center? Why are there so many losses? Well, first of all, there's a lot of cooling infrastructure that is in place to keep everything cool. I talked about that. But there's just a ton of electrical infrastructure. It accounts for about half the cost of a data center. There's all the electrical infrastructure inside. And why is that? Well, the power you get from the grid is pretty reliable here in the country, but it's not up 100% of the time. So inside of the data center, what we'll do is we'll put in power conditioning, we'll put in redundant paths for the electricity to travel down to the servers, And all of this creates costs. It also creates points of failure. So we keep that in mind when we're engineering. Okay, this transient volt surge suppressor may fail. So we have a redundant line around that as well. So that creates a lot of inefficiencies, creates a lot of cost. It's a lot of copper. And on the energy supply, I think we all know that if you're looking at a coal plant, it has a certain amount of efficiency and a certain amount of sort of carbon that's associated with that. If you're looking at wind turbines, that's another deal. But in terms of the national average, the power generation is about it loses about 2/3 of its energy right off the bat, and it's because of the type of engines that are used in the power plants on the grid. So most of them are heat type engines, a turbine, a reciprocating engine, and some of the most efficient power plants out there are the gas turbine combined cycle. So while the turbine cycle loses a bunch of that energy and heat in these very large plants, it's very efficient just to take that heat and then run that through another turbine and get even more electricity out of the same unit of energy. So you can reach some pretty high efficiencies. The problem is you need to build a huge power plant. So that's the bad news. Things are real inefficient, but there's hope, and that is with this fuel cell technology. So a little story. When I was in the Navy, I was in the submarine fleet, and since when I was a junior guy, one of my jobs was to go down inside the battery room, climb down the battery room after taking off all my metal, all the belt buckles and everything, and I'd have to take the gravities on each cell in each battery. So I'd walk up to a very large battery, 2 or 3 feet tall, and it was a glass jar full of acid, and I'd have to analyze the chemical in there to make sure it was still healthy. So what's happening when you're discharging from a battery, as Dr. Norton explained, is you're actually depleting the chemicals that are in there. I remember thinking to myself, well, this is stupid. I mean, once the chemical's depleted, rather than recharging it, why don't I just drain the chemical and put in a new chemical, right? Well, here I am, and here is fuel cells. That's essentially what we're doing, is you've got this battery, and instead of recharging or replenishing that chemical with electricity by charging it, we're just replacing that chemical. In the case of fuel cells, today they're connected to a gas line of some kind. So what's kind of the fundamental differences? So on the left here, this is your basic internal combustion engine. At home, you may have a backup generator, or there might be power plants, other type peaking power plants that are reciprocating engine, and essentially, there's about 4 cycles, and like I said, it's a heat engine, so it's limited by something called the Carnot efficiency. It's essentially running off of explosions, so there's wear and tear on the engine over time. Contrast that with a battery or a fuel cell where there isn't any moving parts. You're essentially just taking a fuel and blowing it through some plates, and those plates are making electricity. Very, 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 very efficient and very low on wear and tear. So an energy generator that has high reliability because there's so much less wear and tear. That's something that's very, very important to anybody who runs a mission critical facility, especially data centers. So how far out is this technology, and when can we start utilizing it? Well, we're actually doing it now in our labs. So there's a picture in the upper left-hand corner of a server rack. Again, this is just a shelf full of computers. Nothing special about it, except that I told you earlier that all computers run on DC. Your laptops, you plug it into an AC outlet, but that little box there converts it back to DC. The battery that's plugged into it is DC. The fuel cells, the voltage that they produce is DC because it's just like a battery. So what we're doing is just keeping everything DC. We're not losing energy when we go from the conversion at the power plant from DC to AC and then back down to DC. So right off the bat, we enjoy an energy efficiency savings by keeping everything DC. Also, keeping everything closely coupled within the rack, we have a whole lot less losses. They're called I²R losses. We have a whole lot less losses just in distributing the energy a few feet rather than hundreds of miles. And things are actually working very, very well. One of the issues with fuel cells is like a battery. The more load you put on a battery, the voltage starts to come down. And with sensitive electronic equipment, you need to keep very, very tight windows. Unfortunately, or fortunately, the server manufacturers recognize that the grid power will fluctuate, and not in this country, but in other countries. I always got to be careful not to offend the utility guys in the room, but not, say like India, for example, the frequency and the voltage, it fluctuates widely. So server manufacturers create server power supplies that can take a broad range, and inside they will, inside the power supply, they'll actually modulate that power quality so it's nice and clean right into the power components. So we just tried it. We just plugged the power supply right into the fuel cell, turned it on, ramped the fuel cell up, did a few perturbations, dropped it down to 0, up to 100%, and the power supplies and the fuel cells are able to work together right off the bat in order to create a very clean supply, or a very high quality energy supply to the servers. Worked very well. Essentially what we're doing is this line of the supply chain at the upper chart here. We're taking the entire energy supply chain from pulling the fuel out of the ground, transporting it to the refinery, refining it, generating power, substations, transmission, distribution, and then inside the data center, all of the backup infrastructure, all of the power infrastructure inside the data center, or we're essentially collapsing it down to the figure on the bottom, or essentially just taking a fuel right inside the data center, right inside of the rack, making electricity, and then supplying it to the servers. Let's see, to find out more, we've got some different press releases and blogs online that you can read more about this. And I'll be available later if you have any questions. Thanks.
Thank you, Sean. Now Dr. Norton's going to give us a presentation on the status of storage technology for our consumer applications.
Okay, thanks, I appreciate that. So what I'm going to talk about is the battery technology for consumer electronic handheld items, and look primarily at what's happening with lithium-ion battery technologies. If you remember from the Rigoni plot, that's the technology that's the furthest to that top left-hand corner of the plot. So as a consumer, you're just thinking about the device you have and what it does and what it doesn't do. And so ideally, there's many things that you really want to have with that device. You want to have high quality screens, you want to have a fast processor, as Sean said, you want to have all these functions that you can use, GPS, cameras, lots of different apps, you want to be able to run them all simultaneously. So the consumer's very demanding. And the battery technology is trying to keep up with what the consumer wants, but also what the designers of the phones and the technology want. And one of the things they don't want to have to do is to worry about the battery life. So they want to be able to do all these things that give great technology and not have to worry about how the energy is being provided to do that. So if you look at over time, you can see historical trends related to battery technology and its impact on portable electronic devices. And so if we start out in 1985 with the Sony Walkman, which at the time was really a pretty cool thing to have, and certainly is, I didn't have one. I mean, they're really expensive, but it's pretty difficult to afford one of those. But it basically ran on alkaline batteries. It lasted about 4 hours. It was just driving the tape player around. And over time, different battery technologies were developed and they were incorporated into these portable electronic devices. Now, if you look at the data on the upper part of the figure, what you can see is with each different new generation of battery technology, eventually it reached the maximum capacity that it could obtain, and it was necessary then to look at another generation of technology to advance what's happening in the bottom figure towards the right, towards getting better technology, lighter, faster, whatever the requirements are. So nickel cadmium is that blue line, and it kind of maxed out around 1990. There were no improvements in that technology since that time. Then you look at nickel metal hydride. That technology was introduced in the mid-1980s, and there were lots of improvements up till around 2000. Then that technology just maxed out. It wasn't possible to make it any better than it was. And lithium-ion batteries came in around 1990, and you can see there was a pretty dramatic increase in the improvement of the batteries with time. And this was due to developments of the different components of the battery, the electrodes and the electrolytes. But around the mid-2000s, we hit a plateau. And so basically, lithium-ion batteries with their current material components have essentially reached the maximum that they can do. Which is why, if you want all these functions on the phone, you have a lower lifetime of the battery. If you want to have a good lifetime of the phone, you turn off the GPS, you turn off these other functions, and you do different energy-saving technologies. So now what we need is a new step change in the technology. And that's got to come about by chemistry. So, we can do all these things with the electronics, but to get to that next level, there has to be a new chemistry in order to do that. So, people have identified a number of different materials that could allow that new chemistry. And so, one of the parts of the cell I want to look at, because it's the part of the cell that we're working on, is the anode side of the cell. So, right now the technology is graphite. It's basically using a pure form of carbon, an engineered form of carbon. And if you just look at that middle number that says maximum capacity, it doesn't really matter too much what the units are, but if you move from the graphite towards the other end of the chart, towards the left side of the chart, you can see that number increases. And that's a good thing, because that's the energy that's available to you as a consumer to operate your devices. So where we're looking at WSU is in tin, which is 3 along from carbon, and that's got a capacity little under 3 times what the existing carbon anode has. Now, when you're using the phone, just to put this in the context, when you're using the phone right now, I can see people texting and tweeting. When you're using the phone right now, you're driving the lithium ions from the anode to the cathode. So you're doing chemistry right now, even though you didn't know it. The lithium's in the cathodes, in the anode side, in the carbon, and it's going across to the cathode. So the more lithium, in principle, you've got in your anode side, the longer you can do your tweeting and phoning, okay? So you can see that by moving to tin, we actually would have a significant increase. And if we could get, say, for example, to silicon, we'd have a 10 times increase in the amount of lithium that's stored in the anode that's going to be driven to the cathode as you talk on the phone. So we can have the next one. Now, one of the challenges is people have identified these materials, and these, again, we have a long history. These materials have been identified many decades ago, so it's not that this is something new that we've come up with tin or that we've come up with silicon. But the challenge is that when you put a lot of lithium into your anode, what happens? It expands. You're putting a physical object into a physical space, and when you do that, the more you put in, the more expansion you get. It's like a sponge swelling when you put water in that sponge. So the challenge that everyone has had since these other materials were identified was the fact they weren't stable. When the lithium went in, it's driven back out, went back in again, the material would degrade, the performance would die, and it wasn't a viable technology. So a group at Stanford University said, well, if you could constrain that massive expansion in a tiny physical space, you can have the stability that you need for repeated cycling. So the structure that they said is you want to have a nanowire. And a nanowire is basically something that's a few nanometers in its diameter and maybe several microns in length. It's got an enormous aspect ratio, many thousands of times. So go to the next one, Michelle. So we were looking, as I said, at tin, and so the trick was, how do we make tin into this structure that we know is stable? And so we developed this technology that allows us to make these, what we call tin nanoneedles. And to give you an idea, the individual image, it shows a single nanoneedle. It's about 50 nanometers in diameter. So to give a context, 5,000 of those side by side would fit within an individual human hair. So that gives you a sense of the dimensions that we're working on. And the image on the left-hand side shows a mat of these formed on copper, which is the current carrier that's used right now to support the carbon that's in your cell phones and tablets. So you can have the next one. So we came up with a way of accommodating this very large volume change in these nanostructured materials. Now the challenge has always been with nanotechnology is how do you get it into a low-cost, industry scalable way that actually allows you to use the benefits of having those length scales, those small length scales, using these materials. So what we've been doing, spending a lot of effort on doing, is scaling up the process so we can go from what would be acceptable within a university to what industry really needs. And so now we're at the point where we're coating these structures onto sheets of copper that are about 65 centimeters by 7 centimeters. So why is that size important? That size is important because at that size you can make these 18650 cells, which are the AA size cells for lithium-ion batteries, and you can also make the pouch size cells, which are the cells that go into the cell phone. So what we're looking at is developing a technology that we know from the scientific point of view works, and then integrating that into a way that it can be manufactured for commercial applications. So in terms of where is this going to go beyond where we are right now? So everyone knows we have to have a new chemistry. Our plan is that chemistry can be lithium with tin, and we have all the data that shows that that's viable. So where do you go beyond that? Because that's only going to take us maybe 3 times better than we are, but then soon the manufacturers of the phones are going to want to even be 10 times more, or even beyond that. So where do we go in the next decade plus? And so you may have heard of technologies such as lithium air batteries and lithium sulfur batteries. So we're still using the basic lithium ion chemistry, but now we're changing the way that we do those reactions. In the lithium air case, we're using air as one of the electrodes. So this sounds great, right? I mean, you're using air. Air's everywhere. But the challenge is that you have to have the air going in to react with the lithium, but you can't have any moisture. So how do you get air to go in and no moisture to go in? And no one's figured out how to do that. So we know that this cell works, but we don't know how to make it. So it's not a science problem, it's an engineering problem. The other example is a lithium sulfur battery, where we do the reaction with sulfur. We react lithium with sulfur. But we keep talking about lithium. Is lithium as far as we can go? Well, a lot of people say no, because what do we know about lithium? From the 101, we know that lithium's the most easily oxidized metal. So we know that it wants to give up its electron, but it's only got 1 electron to give up. But what about if we use magnesium? That means that we've got twice as many electrons for 1 ion that goes from the anode side to the cathode side. But what about if we used aluminum? Then we've got 3 times as many electrons. So the technologies that you're going to hear about are going to be, how do we make things that we know work, like lithium air and lithium sulfur? How do we make them in a way, as was said before, where they're cost effective and of course safe? And then how do we incorporate some of these other elements that have more electrons that they can exchange, because we know from a thermodynamic principle that for each electron, if we can double that, we're going to get twice as much energy for a single ion to move within that circuit. We'll go to the next one. So the opportunities as you look to the future, as part of what we were sort of, our task was given as the presenters, I think, we know that for next generation battery technology, it has to be solved using nanomaterials. I mean, probably many of you have heard about nanotechnology and its, potential applications, and many of you are probably skeptical because very little has really come of a lot of that discussion. But in batteries, it's got to come from that approach. There's no other way to get the energies that we need, the powers we need, without using materials in these very small scales. What we're looking at is the flexibility. I mean, many manufacturers want to have fully flexible electronics, which means that the battery itself has to be flexible. So using the processes that we're developing, we can make the battery onto cloth and fabrics and wearable materials. And that allows you then to have the ability of having fully flexible cells, even wearable batteries, which is the goal of agencies like NASA and the Department of Defense. But then you have to look at the sustainability of the materials that you're using for the battery. And of course that issue's already been raised with the scarcity and the very localized distribution of lithium reserves. And so developing technologies with materials that are sustainable is very important. So the barriers as we go forward, I think the safety always has to be a big issue with any battery, because you've got energy there. And that energy wants to do something. And if we're putting more energy density into the battery, then we have to be aware of safety issues. So if we've got 3 times as much energy in that battery, unless we're controlling the way that energy discharges, you can end up with potential safety problems. And I think as being part of this sort of chain of battery technology from the university lab, from the research lab, in order to get a technology into the marketplace, you have to have adoption of the entire supply chain, from the individual materials manufacturers, the way the cells are integrated, to then the users and the consumers of the technology. So it's very important to have that full integration all the way through that supply chain. Now, if you look back to this plot, what you can see is that new technologies when they come in, are typically marketed for 10 to 20 years. So what we're looking at is what's going to be the technology that's going to have this step, that's going to be maybe the technology for 10 to 20 years, which is typically the time frame where people, for example, with lithium air, if you looked at the lithium air technology, which is 10 times better than the current technology, if you just compared the energy density. Most labs, national labs, NREL, these different organizations, will say that technology is probably 20 years away from being realized. Even though we completely understand the science, just to solve the engineering problems could be 20 years. So what we're saying is the technology that we're proposing is that 10 to 20 year bridge, while these other technologies are developed and then made into the commercial viable technology. So we can just keep clicking until we get all the little pictures. So what I wanted to do was finish. I was asked to finish with sort of a view for the further future. And I wanted to bring this back to the discussion that Sean had about fuel cells. So fuel cells are an example of a flow battery. The example that Sean gave is using fuel cell technology that relies on hydrogen. Now, I think there's lots of benefits there, but imagine if you had a fuel cell that could run on anything. Any source of hydrocarbons could be the source of fuel for that fuel cell. So you didn't have to rely on hydrogen. You didn't have to rely on methane. You didn't have to produce an alcohol. You could use anything. Well, one of the things that we've been doing in my group with support from Boeing is looking at fuel-flexible fuel cells that can produce high powers. And so, as was mentioned by Sean, fuel cells are incredibly efficient. So, for example, typically a fuel cell is using 75% of the bond energy in the fuel is used to produce electricity. Those are incredibly high efficiencies compared to, for example, a coal-fired power plant has an efficiency of 35%. An internal combustion engine, as Sean said, limited by the Carnot cycle, is about 25%. Imagine an efficiency of 75% where the product that you produce is water, you have lower emissions, all of the toxic chemicals like NOx emissions, things like that. So you've basically got a non-polluting system, and it's completely silent. And imagine you can fuel that on anything from gasoline to bio-based aviation fuels to hydrocarbons made from woody biomass residues that are abundant in many different places, or you can use them from any other source of bio-based fuel, and you're using them at an efficiency of 75% of the energy density. So I think as Microsoft is doing, I think it's time to relook at fuel cells as an important component for energy storage, electrochemical energy storage. And just the thing with Boeing, what they showed in some of the analysis they did is even if you use the fuel cell to replace an existing gas turbine engine, and you run the fuel cell on the same fuel that you were running in the conventional engine, you can save 75% of the fuel. So even if you're using fossil fuels, you're going to use them more efficiently if you run them through a fuel cell rather than conventional ways of making energy from combustion of fossil fuels. So my sort of view is that, batteries, I think we're making good progress, but we've still got these incremental changes that have to happen. But I think the work that Microsoft is doing and others are doing, looking at fuel cells, I think is really an important step forward. So, thank you.
Thank you, Dr. Norton. We now have about 10 minutes for questions. I'll take the moderator's privilege and open with the first question. And this is really for Craig. The Federal Energy Regulatory Commission recently came out with Order 792, trying to allow batteries to bid in look at the capacity markets. And I'm curious from the utility perspective, though this does filter down to whether you're a commercial or even a resident that's looking to do battery storage with your power system, is there's a lot of different, you had a whole list of value that a battery can add, different services a battery can add, but monetizing all those is incredibly difficult under the current regulatory regime. I wonder if you could sort of address how the FERC order changes or doesn't change that, and how your utility is looking to monetize the benefits of batteries as they come online.
Sure, yeah, that's a really good question. In fact, there's a lot of things going on right now that hold the potential to really transform the energy storage industry. The FERC order is one of them. FERC, of course, is very market-driven. There's no lack of angst at FERC that we don't have a formal market out here in the West, and there's a lot of work going on right now in the power pool and other places to cause that to occur. So right now, all of our ancillary service and energy transactions out here in the West are largely bilateral. There's not really a market. But there is a lot of movement afoot right now to establish first an energy imbalance market in the Northwest and in the West that could eventually turn into an ancillary services market. So that's probably the point at which some of these FERC market-driven mechanisms would start to affect us. One of the biggest things in the energy or the battery energy storage industry nowadays that we didn't talk about was really the California mandate, 1.3 gigawatts of new energy storage they're targeting by 2020. That is huge. That's massive. That's a sea change in the industry. And one of the interesting things they did in that legislation was require that it be cost effective. So cost effectiveness, of course, is often in the eye of the beholder. It's yet to be seen exactly how they kind of craft that cost effectiveness metric. But that's the thing that we're really watching closely. In fact, we're a member of the group that's engaged in some of the work going on down there and have established a lot of comments on that effort. Because one of the things that we're cautious of up here is, any kind of an unfunded mandate to a utility, isn't always, we would say, in the best interest of our customers and our ratepayers. So that's one of the things we are trying really to do with the MESA project is show folks down in Olympia and others here that there are a lot of different ways to look at cost effectiveness, and we really should be focusing on, what are the ways in which we can do that in a way that's going to be cost effective and really durable and sustainable for the long haul. I don't don't think so, because I think the way the process is going to work down there is sort of an RFO process, whereby utilities will put out requests for offers that really sort of delineate what they want, what they're looking for. And then I think the question is out there whether or not how the market responds to that. It's not just battery energy storage that can meet that. Pumped hydro less than 50 megawatts will count. Compressed air storage will count. So there are other ways to get there. I would sort of guess that probably guys like Russ and Tom have spent a lot more time looking at and thinking about that California market and how that might be met than we have even. So good guys to follow up with.
Yeah, this question is for Sean. Is Microsoft and other fuel cell customers requesting solutions from fuel cell manufacturers to harness the waste heat that's being expelled by these fuel cells?
Yeah, that's a great question. So one of the biggest problems with data centers, we're trying to get rid of heat. We don't really have a need for heat. But, however, what I showed up on the screen there, that was about a 12 kilowatt fuel cell. That'd be perfect in a home, right? I mean, you can imagine something that's roughly half the size of a refrigerator. Not only are you making electricity, but you're also making heat. I think it would be a great application, a micro CHP application in the home. And they're already doing it in Japan, starting to do that in Europe. And I think that it's a matter of time before we start seeing these very small fuel cells in our own homes. I think it's a great, I'd like to have one.
Right. And most of these fuel cells sit outside the data center, like for instance, a boom box, expelling that heat when it could be captured by something like a Stirling motor and converted into energy.
Oh, absolutely. So if you can't hear him, he's talking about what can you do with the heat that's coming out of the fuel cell. And the National Fuel Cell Research Center at UC Irvine actually experimented with taking that heat from a fuel cell and running it through a turbine. This was 5 or 6 years ago. And they were able to demonstrate very, very high electrical efficiencies, like above 70%. Yeah, his question was about flash storage. What flash storage is basically a USB drive or a little memory card that you put inside of a camera. If it works great for a camera, why can't we do that in computers, right? Instead of the typical hard drive where there's a little platter and they're spinning and it's prone to failure. That is the future. I think it was Panasonic or Sony recently just announced they've got a 1 terabyte flash hard drive. One of the problems with conventional hard drives, I know this isn't hard drives, but I'm a geek, I love this kind of stuff. Anyway, what happens is when you're recording data to a spinning drive, you actually, when you write to the drive, that's fairly quick, but when you want to read from the drive, you have to a lot of times wait for that platter to come back around to the same site. So the read speeds on hard drives is some sort of slow. You might notice that on your computer when you're trying to access data, it takes a little. Well, flash drives, it's instantaneous because there's no mechanical issue with it. In terms of energy storage, there isn't anything spinning with the hard drive. So I think it's the future.
So I'm intrigued by the example Mr. Sprague gave of the how much cheaper the Nissan Leaf with the battery included than a standalone battery. It seems like this, as the folks know, Washington companies were pioneering a number of years ago, looking at ways you could integrate electric vehicles and actually the storage units in the grid. Is that something you still see as being an important opportunity, or are there challenges in making that happen?
I think it's a long-term opportunity, perhaps. I think that the EV market has slowed down from what folks might have thought it would have been a few years ago, but eventually you could definitely see that becoming part of the landscape. Mostly what we tend to look at nowadays is trying to keep a close eye on where we might end up with clusters of folks, customers who have EVs. And really, it's not so much a problem of energy delivery, it's really just the robustness of that local distribution network to help make sure that we can provide energy during those peak times. And from an energy standpoint, many years probably before we at least would envision that kind of moving the needle or to be much of a factor for us.
Follow up to that before I get to Russ's question. The current, because I've heard this from a couple of people trying to integrate EVs to design sort of small house microgrids. With current EV technology, can the battery discharge into the home? If even in that situation, say you had that for the current cars, will that destroy the battery, destroy the cars management system? Are they designed for that application currently?
You know, there's probably better folks even in the room than me to answer that. What we get concerned about from a utility standpoint primarily, I mean, really for us it's all about safety and reliability, you know, so anything that starts to interface with our grid that we're going to have our folks working on or that our customers are going to have, you know, on their home, it just absolutely has to be safe. And regardless of whether folks have their own, you know, kind of microgrid or their home storage system, they still want reliability, you know, they still want the light to come on whether or not their system is functioning or not. So for us, you know, our mission, what you know, keeping our eye on the ball really means for us is, you know, safety and reliability and cost effectiveness in terms of meeting our customers. So that's really the landscape against which we sort of gauge all of these different sorts of things.
So one thing quickly, Ross, Panelists does some interesting work in terms of discharging from these, but not necessarily charging because of the battery manufacturer warranty issue. So, like the fires, so question though for Sean. So you're using natural gas fuel cells, correct?
The demonstration project, just to prove the technology, that's a hydrogen fuel cell. However, hydrogen is an energy carrier. It's not really a resource. You don't really go out and mine for hydrogen. So the future it's going to have to be methane natural gas until this hydrogen infrastructure that we've been promised comes about, or not. You know, but either way, I think that I showed a PEM fuel cell. That's something that you would put in a vehicle because it reacts really quick to load changes. A solid oxide fuel cell is much better because it's much higher efficiency. The problem is it's also much higher heat. It's 800 to 1000 C. So for you to go from half load to full load, that thing needs to heat up, and it takes a long time. So I think the future is actually low temperature solid oxide fuel cells. I think the DOE agrees. They recently announced a funding opportunity to fund low temperature solid oxide fuel cells. You get the best of both worlds, the really quick dynamic load change of a PEM plus the fuel flexibility of a solid oxide. And a quick story or a quick thing about the using an EV vehicle or a hybrid vehicle to charge the home. A number of years ago, I think it was somebody in Seattle during that very extended power outage. I read that a guy actually plugged his Prius into the house, and the battery would keep the lights on in his house, and then the engine would automatically start up at night and charge the battery. That was really cool. If the things were still running today, I have no idea. He might have killed the whole electronic system, but that's really cool.
Okay, mine is on the macro scale, and for all of you, because what I saw throughout each presentation was a disruption in the current market. You're looking at something that's going to disrupt some part of that. The fuel that things are coming from now, or the distribution system, or millions of wires out there, or something. As these, just storage in general, regardless of the form, battery type, begins to be more sophisticated, more efficient, is this a situation where you're viewing the entire energy production market working together, or are you anticipating some kind of, you know, if this stuff really takes off, we're not going to be looking like we do today as far as, you know, right now we're bringing fuel out of the ground, we burn it, we make it electricity. That's still part of the system. Is storage or the chemistry that's being looked at here something that could ultimately replace, you know, big vision? Is this where we may end up?
So my opinion is I think that the future is distributed energy, and I think that a lot of people see mini power plants in their homes in the near to distant future.
And I think if you look at it, the use of many renewable technologies, and the example was given about the variability of wind, and obviously solar is another one, the development of storage technology is critical to the realization of these other renewable technologies, which then feeds into the distributed grid model that Sean mentioned. So that you're right, I mean, they're all completely interconnected, and we can't really do one without the other. As we develop the technologies, we can move to a more sustainable type of energy generation.
We definitely would agree that distributed generation is going to be a big player in the future of the utility industry. And you can go out on you can see all kinds of articles right now saying the utilities are already dinosaurs. You know, we're on our last gasp, and we're done for. We think there's always going to be a need. We think for the larger grid, and there's a tremendous amount of work going on right now to modernize both the robustness of the grid, but also the intelligence of the grid, the ability to take energy from many different sources, at the same time, and integrate them in a seamless way that maintains both reliability and sustainability. So I think it's both the distributed nature of energy that's going to change and the storage aspect, but again, that kind of that control and communications piece that's really completely lacking right now, that's going to be another big change, we'd say.
Our last question.
Yeah, are there any advancements in the way we measure the true state of charge, such as lithium iron phosphate batteries? There's a big disconnect between the current technologies on the market that measure inverters and chargers. They're lacking algorithms that accurately measure the true state of charge. And these lithium iron phosphate batteries, we do a lot of distributed energy for microgrid integration for solar and wind. And we've got some good technology we're using, but we're still losing probably 20% because we don't have the proper integration. There's no accurate way of measuring the true state of charge, how many amp hours are left. That's my question.
So the problem he's talking about is you've got a battery sitting there, and how do you know how much juice is in that thing? And it's a huge issue with data centers, especially with these lead acid batteries, because in order to test a battery, you actually degrade it, you destroy it a little bit. And I have not seen any significant advancements, especially as it relates to lead acid batteries and measuring the true state of charge. Just that it's kind of ironic that this battery, in order to use it to test it, you actually destroy it. And it's one of the big issues inside of data centers. And since it's a chemical reaction inside the battery, temperature is a big deal also. We actually have to keep the batteries in a separate room that has a much more tighter operating envelope than the servers. We just use outside air to cool the servers. We have to condition and coddle the batteries to make sure that they're available when we need them and we don't destroy them. I haven't seen anything.
So my job is to clean up here for a second and introduce Susan Betcher to close things off. So I'm told there is a raffle for 2 free tickets for our next event. I even have a big sign here to prove it. So Sharon, you're taking business cards, or Kelsey is. There is an exhibit over there of a fuel cell that E-Core has provided right over in the corner. Wave your hand. So take a look at that on the way out. That should be quite interesting. I want to thank a whole lot of people, of course, Kelsey and Sharon, for everything they've done to make this happen. Our organizers. You can wait. You can hold applause until everything. Okay. Avi Jacobson, of course, Andrea McFadden, Travis Woodland, and Russ Wheat were instrumental in putting this together. Of course, Perkins Coie, Susan Betcher, and Pam Anderson. Our next session is going to be entitled the 2014 WCTA Crystal Ball, Forecasting the New Year. It'll be a little bit longer. We're going to have 2 sessions. The first one we'll have Dave Beck, who's over here. Wait for you, Dave. Don't clap for him, though. And Chris Thanker from Merrill Lynch talking about the economic outlook for the year. And then we'll have a panel that will include Todd Myers, Richard Locke, Brad Boswell, and Chris Jemian looking at the political forecast going on during the course of the year. And just one last question. How many people here had their birthday yesterday and went to the Macklemore concert? Anyone? Oh, Susan Betcher.
Yep. So I'm a little sleepy this morning. So thank you all for coming. Bruce Dick and I are co-chairs of our firm-wide clean technology group, and I'm really excited that we have the opportunity to host this. And these are important conversations that we need to be having. And I think the question and answer there's several people in the audience who'd like to continue to have that discussion. So hopefully you guys can stick around a little while. I'm looking forward to seeing all of you on the second Wednesday of every month going forward into the new year. So Tom just gave us a look into our crystal ball for the future for our first breakfast in the new year, but every second Wednesday of the month going forward, we'll have breakfast together and have some important discussions. And your criteria for whether you successfully did you learn your new thing?
I learned quite a bit today. Yeah.
Okay, that's Tom's rule. He has to learn something new at every event he goes to.
And tweet a lot too.
Okay, so thank you all very much.
Great to see you.
Well, then, I on that deal with GE, shooting her out from Aiken. When she left Aiken, I left Stoll. So you're all doing that deal. We're railing left and right. Oh, yeah. Well, we got, did you leave just before it got signed? Yeah, okay. So I left right after we got it signed out. Actually, no, I'm in Canada. It looks like we had a whole What's that? Oh, it's great. It's up to the team. You have business here locally. Yeah, exactly. Everything excellent. Projects right now. Has no presence where the market is we actually already have a national this is their effort. They're trying to break out of that. But anyhow, that was largely it. I was able to be able to I like what to hear. It's all about the makers. Yeah. Great. Yeah, sure. Yeah. Oh, okay. Okay. Who's been using helping them do something? Yeah. It does. Oh, so they're getting their billing system. Yeah. I know we have to work at Yeah. I'm every time they just talk about the number of their projects and things, and we just have a chance to sit down and move forward. And I think that some other folks like particularly down in Cornbury, just storage is what we're talking about. Yes. All right, hey, great to see you again. Yeah. again, it's one of my goals that we didn't really get to get sales. I want to spend time now we're recording, so you don't know, you never know. In the short term, it will cost us a little bit more money. It's still going to be not only nice finished product that we sell us, when we bring vendors, when we bring sales guys in that we want to hire, then we've got a better start using that instead of using like a price. All this type of products. So once they're developing marketing materials, I want electronics, software saved to my laptop, so that I can start creating materials. I will start creating what I need are labels on whatever photos I can reach by. This is what this is. And I'll just put it in a file, and then I'll start working on so they're making noise without any background. So, but yeah, did I hear
Let me just finish one comment. Great to see
And you want to go that's
so my work you have any issues? All right, I got a full day today. Email me in. I'm here until 3. I'll be there a week. I'll be there. Yeah. I won't talk. That's
Yeah.
you know, it's a little bit, I know that that's a little style. How much charge That's what I'm saying. I'm sure
And the only way I can think of is if someone could integrate life science batteries, while it's being made, magnetic frequency,
I understand. Yeah, you want to do it. How much remaining? Take the cap out, pull up the thing, the bulb in there. Right, but I think it's, like I say, I'm with it back. I haven't seen what type of battery it is, but like I say, talk to the manufacturer. You go and listen, you want to be able to know how much life is they can have that. That's a feature that could be important. You talk to them and see if they can incorporate that feature. Right there, the that's funny right I'm surprised that they're in charge of the so what do you guys study? It's at 75%. You want it down here, it's 25%. So when the plane takes off,
I am.
That's only for the budget for performance. Well, last week you're talking, but you're not talking actually driving it. Oh, okay, well, I wasn't clear on that, so it's only for the maximum performance on someone's. So really, it's, you're not concerned about the fuel savings. How much, what percentage of the fuel that we use the source? 1
Oh, I wrote that on the thing. I didn't notice something where I had what you have to do is you have to spread.